Okay, we're going to briefly review a really classical algorithm for graphical model inference, loopy belief propagation. Loopy belief propagation is derived by considering an algorithm that is correct for tree graphs. So in the case of tree graphs, you can compute the partition function and the marginal probabilities exactly using a kind of dynamic programming algorithm. So in Loopy BP, we take the dynamic programming algorithm that works for tree graphs, and we just, as a matter of faith, use the equations that you get for computing messages. It's a message passing algorithm, and you just use them for loopy graphs, for graphs that contain loops. And this algorithm has proved to be quite effective in something called low density parity codes in communication theory. When you send a message from a satellite over a very noisy channel or from a deep space probe, you add parity bits to correct mistakes that are made in the transmission. And you have to do this inference problem to the most likely message that was actually sent. And Loopy BP proved to be extremely effective. The graph you get is loopy in finding the correct, using the parity bits to recover the message that was originally sent. Anyway, it has proved to be effective in important applications. So we're going to take an algorithm that's correct for trees and adapt it to the loopy case. So the algorithm that's correct for trees involves messages sent between the nodes of the tree. And the message that you send between two nodes, say I'm sending a message from 4 to 5, is the partition function for the subtree attached to 5 through that edge. So the message from 4 to 5 is going to take each particular value of 5 and compute the sum over all colorings, all labelings of this subgraph with that particular label assigned to 5 of e to the score for those labelings. That's the partition function for a particular value of 5 for the subtree attached to this message. And we're going to do that for all messages at all edges in both directions. And we're going to use a dynamic programming algorithm that computes this message from the messages coming into 4, into the preceding node. So I'm going to describe in words how that message is computed, and I'll let you verify that the equation written down here corresponds to what I'm saying in words. So we're going to compute a message from 4 to 5. The message from 4 to 5 is going to have a value of a partition function for each possible value of 5. So this message coming in here is a function of the possible values of 5. So for each possible value of 5, we're going to compute the value of that message by summing over the possible values of 4. We have to consider all possible colorings of this thing. So we have to consider all possible colorings of 4. But rather than computing all the possible colorings of all the, explicitly computing all the possible colorings of all the things connected to 4, we're just going to take the messages that come into 4 and for any particular value of 4, we're just going to multiply those messages together. And that corresponds to the fact that the colorings now of the subgraphs attached to 4 are independent, because this is a tree. So the coloring of the tree attached to 4 here is independent of this one's independent of this one. So we can get the partition function for a particular value of 4 by simply multiplying these messages together. So again, to get the message for 5, we sum over the values, to get the message for a particular value of 5, we sum over the particular values of 4. For each particular value, we take the product of the messages coming in here. We then add the unary potential for 4 and the binary potential for the pair of values 4, 5. And we add that all together for all the possible values of 4, and that becomes the message at 5. And if you want, you can pause and verify that what I just said is this equation. Okay, now that, what I just described is exactly correct for trees. Now we're going to do it for graphs with cycles. And for graphs with cycles, what we're going to do is we're just going to initialize all the messages to be 1. So we assume that we've got a message in both directions at every edge. And we're going to recursively compute, use the equations essentially that I just showed you to compute the messages from the messages according to the equation I just showed. And we're going to repeat that over and over again. And hopefully the messages will converge. That's a little tricky. And then we'll use those messages to get the marginal, or to estimate the marginal probabilities that we need to do our graphical model inference, to backpropagate across the exponential softmax. Okay, but there's an issue when we use these equations recursively and iterate them. If we just did that naively, these partition functions would diverge to infinity. So what we're going to do is as part of this update process, we're going to normalize the messages. So I'm going to write z tilde for the normalized message from m to n, where y is a coloring or a label of n. And I'm going to do that simply by defining a normalizing constant, which is the sum up over all possible values of all possible labels y for the node n. So, and normalize it by dividing by that normalization such that this becomes a probability distribution over y. So I'm normalizing it to be a probability distribution over y. And then in the equation to recursively compute the message from m to n, this is the equation I had before, but instead of using the unnormalized message here, which would be computing for trees, would be computing the exact partition function, I'm going to use the normalized message, such that this, when I recurse on using the messages, I use the normalized messages. And you can show that if this was a tree, this normalization would still yield the right answer. So for trees, the normalization doesn't change the answer. And in the loopy case, it keeps everything finite. It keeps the normalized messages are probability distributions. All right, now we still have to get the marginal probabilities. So again, I'm just going to do this in words and leave it up to you to verify that the equations are correct. If I want to get the marginal probability of the possible values at node 4, so pick a node like 4 and say, what's the probability distribution over the various values at 4? Well, what I'm going to do is I'm going to pick a value at 4 and multiply all the messages coming in. And that's going to give me a partition function for the set of colorings that have that color for 4, right? If I take the product of all of the messages coming into 4 for a particular color of 4, that's the partition function. It's the sum of e to the score for all the labelings that have that labeling for 4. Now to get the probability for 4, I just take that partition function and divide by the total partition function. And that gives me the probability of a particular label for 4. And you can verify that the equations I've written below are that. Now we can do the same thing. We also need the marginal probabilities for pairs across edges. So I need the marginal probability that 4 has a certain value and that 5 has a certain value for this edge. But I can do exactly the same thing. I compute the partition function for the case where 4 has a particular value and 5 has some particular other value. And I can compute that partition function by multiplying together the messages coming into 4 and the messages coming into 5 for this particular pair of values. And then again, I can divide by the total partition function to get to make it a probability. And the equations for that are on this slide. Again, I'll leave it to you to verify that these equations are what I said. It's kind of magic that English works better than equations sometimes. Anyway, thank you, and we'll stop there.